Welcome to AA204 and the course name is Analog Electronic Circuits. This is the first and the last class of 1995. Isn't that right? 29th December 1995. So our next meeting would be 1 year later. This is my name, S.C. Datta Rai. I am a professor of electrical engineering in this institute. The course contents as listed in the bulletin. This item is missing. This is what we will start with, review of DC models of devices, and these devices basically are junction diodes, BJTs, bipolar junction transistors, and FETs, field effect transistors. You have been acquainted with them in EE110, that is Introduction to Electronic Circuits. Have I told the number correctly? 110? Yes. We will review that knowledge basically from the surface, not going into very deep. Then we shall review transistor biasing. This also you have done earlier, but we will bring in quantitative measures of bias stability, like stability is the term. Then we shall discuss current mirrors and their applications, small signal amplifier design. Little bit of this you have done earlier, RC coupled amplifier, its frequency response. We will go into other kinds of amplifiers in much more details. We shall discuss power amplifiers in details, the frequency response and wide banding techniques, that is, given an amplifier which has a certain bandwidth, how can you increase the bandwidth. We shall discuss feedback amplifiers, tuned amplifiers, amplifiers which resonate at a particular frequency, that is, which responds to a particular frequency and a small band of frequencies around it. These are tuned amplifiers. We will discuss oscillators, that is, signal generators, circuits which generate sinusoidal signals as soon as the power supply is put on. They do not require any external input. Then we shall discuss rectifiers, some of which you have done, diode circuits you have done earlier, rectifiers, power supplies and voltage regulators. Along with all these circuits, we will discuss both BJT, bipolar junction transistor, and field effect transistor circuits, FET circuits. We shall discuss the most important analog integrated circuit, namely the operational amplifier, and other linear integrated circuits, LICs. And finally, if time permits, then we shall discuss noise in electronic circuits. The two textbooks are Barnes and Bond. This is Principles of Electronic Circuits, published by West Publishing Company in the United States, and it's a 1987 book. And the second one is Millman and Grabel. This book is Microelectronics, second edition, McGraw-Hill, 1987. A large number of copies of this book is available in the library, but this may not be available in plenty, Barnes and Bond. If certain portions are needed very badly, I may give you a handout. I may Xerox that portion and give you a handout. But let me assure you, you will not generally require to read a textbook in great details unless you miss the classes and absent the classes. Both are costly publications. This is not available in soft binding at all, the first one. This one is available in soft binding, so I leave it to you whether to buy or not, but the library should be able to help you. Our course of our plan is to have 1 to 3 lectures and then 1 problem solving session, but as I said, we will be flexible in this. and today is the first lecture, lecture 1, and our topic is review of DC models of diodes and BJTs, bipolar junction transistors. First we talk of a diode. As you know, a semiconductor diode contains basically two types of semiconducting materials brought in the neighborhood of each other by metallurgical means, okay, and one is a P type, which is a preponderance of holes, that is positively charged carriers. One is an N type, which is a preponderance of electrons, which are the majority carriers. The P type material also has electrons, but they are in the minority carriers, whereas N type material also has holes, but they are minority. And normally a diode, if a battery is connected like this with positive connected to the P side and negative to the N side, then it is said to be forward biased. Okay, this diode is forward biased. And if I denote the voltage across the diode, I might have a resistance here. If the voltage across the diode is denoted like this and the current is denoted like this, the current naturally shall leave the positive terminal of the battery, enter the P type, and then go out of the N type to the negative terminal of the battery. Then the IV characteristic of the diode, to denote that it is a diode, we use a subscript D. Is the writing clear enough on the, okay, VD, to denote that it is a diode, we say ID and VD, and the mathematical equation connecting ID and VD, as you have studied in 110, is ID equal to sum IS e to the power Q VD divided by KT minus 1. This is the equation, basic equation of a diode, where capital IS is a constant. It is called the reverse saturation current. Reverse saturation current. Q is the electronic charge. K is the Boltzmann constant, and capital T is the absolute temperature. Okay, QVD by KT. It is exponential in nature. All right. Normally, at room temperature is usually taken as capital T equal to 25 degrees C. At room temperature, KT by Q is equal to 26 millivolt approximately. At capital T equal to 25, let me recall the relation. I sub D equal to IS e to the power Q VD divided by KT minus 1. KT by Q is usually 26 millivolt. Now, is it clear that KT by Q should have the dimension of voltage? Because the power of exponential cannot have a dimension, that must be dimensionless, and VD is in volts, therefore KT by Q must also be in volts. The numerical value is 26 times 10 to the minus 3 volt, 26 millivolt at 25 degree C. This is conventionally and universally used as the room temperature, as the temperature at which all calculations are made. 25 is a very sacred figure. You will see later on that in order to make calculations simple, we might take this, instead of 26, we might take this as 25. There is nothing sacred about it. You changed the temperature slightly, you reduced the temperature slightly. Okay, 25. to make life simple, to make numerical calculation simple, which means that 1 by 25 will require Vd by 26. 1 by 26 is not a very nice figure, but 1 by 25 is 0.04. It's a very nice figure. So sometimes we will take, many of the time, most of the times we will take it as 25 millivolt. Number one. Number two, why is Is called the reverse saturation current? This is because if Vd is negative, let's say Vd is equal to minus, let's say 0.1 volt. 0.1 volt is how many millivolts? 100 millivolt. So it would be e to the power minus 4. Agree? 100 divided by 25, e to the minus 4. Now the value of E lies between 2 and 3, and therefore e to the minus 4 is a very small quantity compared to 1. So even when Vd goes to minus 0.1, this term goes to 0. Compared to unity, it's a very small quantity, and therefore the current goes to minus Is. The current cannot decrease further, all right, because the minimum value of this is 0. Therefore the current gets saturated when the diode is reverse biased. Even with a very small voltage, even with a small reverse bias, the diode current gets saturated, and therefore Is is called the reverse saturation current. Okay. In the reverse biasing, under reverse biasing, let me write it down, Is e to the power QVd divided by Kt minus 1. Okay. So this is approximately equal to minus Is if Vd is negative. All right. On the other hand, if it is positive, if Vd is positive, suppose Vd is 0.1 volt, then you see e to the plus 4 is a very large quantity compared to unity. What is 3 to the power 4? 81, and 2 to the 4 is 16. Well, 16 is not very large, but 81 is, between 16 and 81. So under forward bias you can write this as Is e to the power QVd divided by Kt for forward bias. Okay, not very negligible forward bias, but sufficiently large, and you will see sufficiently large means that Vd must exceed about 0.7 volt. You will see in a minute. Okay. So under forward bias this is the relationship, under reverse bias it is approximately a constant. And if I plot the diode current voltage characteristic V sub d versus, well, I sub d versus V sub d, the characteristic is something like this. The current is approximately 0 for a certain range, then it rises, and the rise is obviously, it would be exponential. Okay. And it is this region, where the current can be approximated at Is times e to the power QVd by Kt. This point at which the current starts rising is approximately this voltage is approximately 0.6 volt, approximately 0.6. Now for reasons to be clear right now, we take the cut-in voltage, that is the voltage after which it conducts, as 0.7, and the reason is this, that this exponential rise, we don't like non-linearities. Electrical engineers, in fact all engineers, they will try to avoid non-linearity as far as possible. Now a diode, even though the characteristic is exponential, we usually try to approximate this by means of a straight line, a linear rise, and this straight line usually cuts the axis at 0.7, and therefore what we do is, instead of taking the usual model of the diode, usual non-linear characteristic, we make it piecewise linear. That is, we take this as a straight line up to this, and then a straight line going up. This blue line is the piecewise linear model of the diode. Piecewise linear model of the diode, okay? Which means that in the forward direction, when the diode is forward biased, I can model the actual diode by means of an ideal diode. What is an ideal diode? An ideal diode, the current is infinity when the voltage is 0. For an ideal diode, the characteristic is something like this. For an ideal diode, the characteristic is this. That is, ideal diode is an ideal switch. As soon as you apply voltage, it becomes a short circuit. Short circuit means it can pass indefinite amount of current. No ideal diode, by virtue of the adjective itself, can be made in the laboratory. Idealness cannot be observed, cannot be seen. Okay. So what we can do is we can approximate this by an ideal diode, and then what else do we need? We need a battery, because it starts conducting at 0.7, and therefore we will make this a battery of 0.7 volt, okay, and this piecewise linear characteristic can be approximated by a resistance. If I take the slope of this, that is dId dVd, that would be the resistance, and this resistance we will call this as Rd, which is dVd dId, that is the reciprocal of the slope of this curve, alright, reciprocal of the slope of this curve. So this is a model. You see, if you apply a voltage between these 2 points, there would be no current in this circuit till the voltage exceeds 0.7 volt, because the cathode of the diode, the N is maintained at plus 0.7, this must exceed 0.7 in order to make the diode conduct, and this is an ideal diode. Now the ideal diode, the total circuit is a model of non-ideal diode, because we have included the resistance Rd. Okay. In actual practice, well, this will be the DC model of a diode that we shall be using in our discussion of electronic circuits. But in an actual diode, as you can see, ID is equal to Is e to the power q Vd by Kt minus 1. As you can see, dId dVd, okay, reciprocal of this is a function of Vd, isn't that right? Is a function of Vd, and you can show by actual differentiation that this is equal to Kt by Q Id. That's right. We can show by actual differentiation. Well, you have to ignore this term because we are considering the forward direction. We have to ignore this term. Then you will see that this is equal to Kt by Qid. So this is approximately equal to 25 or 26, whatever you take. Let's take 26 millivolt divided by I sub d. All right. Typically, if the diode conducts, let's say 26 milliampere, then the resistance would be 1 ohm, just 1 ohm. Is that clear? Now the reason why I am discussing this diode in details is that the emitter based junction of a transistor or the collector based junction of a transistor, they are both diodes, and therefore if you take the emitter based junction of a transistor, for example, the resistance would be equal to Kt by Q, the base current, okay, QIP. We will come to this later, but the reason why I am discussing this is that the same relation applies in junction transistors also in the two junctions that we talk of. Now let's go back to this characteristic. What we did was we plotted the forward characteristic like this. The reverse characteristic, naturally when Vd is reversed, the current shall also reverse. The reverse characteristic is something like this, and you know that even for a small reverse V sub d, the current remains almost constant at I sub s, that is the reverse saturation current. So this current is I sub s. Is the point clear? However, it is found that if you continue to increase the reverse bias, then ultimately the junction breaks down. That is, at a particular voltage which you shall denote by Vz, at a particular reverse voltage, the current suddenly goes very high. The current suddenly at this voltage, the current goes very high and the voltage does not change. Voltage remains almost constant. Now this can occur due to one of the two phenomena. Obviously in this range, that is if V sub d is less than equal to minus Vz, then this equation of the diode, that is Id equal to Is exponential QV by Kt minus 1, is not valid. This is valid only for the red portion of the characteristic. I have shown this exaggerated. This is actually a very small quantity. Is is of the order of microamperes, some tens of microamperes. That's about all. It cannot exceed more than this. But if you exceed a particular voltage, Vz minus Vz, reverse direction, then the diode breaks down. In other words, the current goes on multiplying itself. The current increases substantially without an increase in the voltage. So it's almost a vertical line. This breakdown can occur due to one of two phenomena. One is called avalanche breakdown. Are you acquainted with this term? Avalanche and Zener? You do? Zener, of course you do. Zener diode for voltage regulation? Yes. You must have used. Okay. The difference between the two, you see the characteristic is more or less similar. The difference between the two is that the avalanche breakdown, well, the avalanche breakdown occurs under high field condition, high electric field condition, okay, and avalanche breakdown, any breakdown which occurs above, let's say 6 volt, a rule of thumb, it may be 7, I mean it may be 8, but rule of thumb is approximately if the breakdown occurs at high voltage, then it must be due to a high electric field. You see, as you increase the reverse voltage, the electric field created in the space charge region also increases, and that might cause a rupture or a tunneling through, so that majority carriers can tunnel through very quickly. An increase of current means that carriers, there are more carriers to carry the current. Okay. So avalanche breakdown is a high field phenomenon. On the other hand, Zener breakdown is a high doping phenomenon. That is, both P and N materials, if they are very heavily doped, then even a majority carrier with a small energy, when it enters into the minority carrier, into the, let's say, when an electron from the N-type material enters the P-type material, it encounters minority carriers, that is electrons in the P-type region, right? Electron in N-type is majority carrier. If it enters with a small velocity into the P-type material, it encounters other minority carriers, majority carriers which are holes, and also atoms which are not ionized, this energy, because it is heavily doped, it gets so many particles to collide with that it sets out electrons free from atoms which are not ionized, and therefore it creates by collision more carriers of current, and therefore the current increases. This is the Zener effect. Okay, Zener effect occurs usually for less than 6 volt. If this breakdown occurs for less than 6 volt, well, you are more or less certain it is a Zener effect. If it occurs for higher values, then more or less it is sure that it is an avalanche effect. Whatever the effect is, if you are a circuit engineer, if your job is not to understand devices but to use them, you don't care. What you care is whether the manufacturers list this as an avalanche diode or a Zener diode. The Zener diode, as you know, is used in voltage regulation. That is, the current can take any value depending on the external circuit, but the voltage remains a constant. For example, if you have, let us say, a circuit like this, a resistance, and then a Zener diode like this. Zener diode is usually indicated by a curved line here. You see, this diode is reverse biased, right? This is the positive supply battery, but the diode is reverse biased. Then if Zener breakdown occurs here, then this voltage will be V sub Z irrespective of what the external resistance is. Is the point clear? Whatever the resistance is, this voltage remains constant, and this principle is used in voltage regulation, that is, in making a power supply whose voltage shall remain a constant irrespective of fluctuations of, even this battery may fluctuate, it does not matter, even this resistance may fluctuate, but this voltage shall remain a constant. Okay? So, in getting a constant voltage supply, a Zener diode is used. The characteristics of a diode are temperature dependent. Okay? This is one of the disadvantages of a diode, but it is also an advantage. If you want to make temperature compensation, it is also an advantage. It is found that if ID is constant, that is, if you drive the diode by a current source, a constant current source, you inject a current ID, then Vd changes with temperature at the rate of minus 2 millivolt per degree centigrade. This figure is important. dVd dt is approximately minus 2 millivolt per degree centigrade. On the other hand, if Vd is constant, then I sub d, Vd is constant, that means you drive the diode by a constant voltage supply, then dId dt is approximately 0.072 amperes per degree centigrade, 0.072. And the rule of thumb is, this figure should also be remembered, the rule of thumb is that the current doubles for every 10 degree centigrade rise in temperature. ID doubles for every 10 degree centigrade rise in temperature. Okay? These two figures are important and one should remember this. In the few minutes that is left, let me remind you of the physical phenomenon that occurs in a BJT very briefly. As you know, a BJT, bipolar junction transistor, has two junctions, and to be specific, let us take an NPN transistor. Two junctions, that is, it is a juxtaposition of two diodes, NP and PN, alright. However, these are metallurgical junctions. These are not simply that a material is brought and placed close to each other. One is, the P-type material is diffused in an otherwise N-type material. The details of fabrication shall be dealt with in another course which you will get in 3rd year or 4th year, that is IC technology. and also the details of devices will be available in another course, an elective called physical electronics. So we will not go into those. What we are interested in is in discussing electronic circuits, analog electronic circuits. We have to understand a little bit of the physics to be able to get a circuit model, and that's where we shall leave it. For example, in the diode we got the circuit model, the DC circuit model, along with the incremental resistance, piecewise linear. Now here we are taking an NPN because NPN is more commonly used than PNP, and also the material that is used is silicon. Okay, so we take a silicon NPN transistor and we denote the terminals as E, B and C, emitter, base and collector. There are 3 terminals, and as you know, the symbol for this transistor is this. Now, do you know the significance of this arrow? This is the actual direction of current into the emitter. For example, the emitter base junction will have to be forward biased, that is, we shall have a negative here and a positive here. We call this a VEE, let us say. A battery has to be connected, a power supply has to be connected, so that the emitter base junction is forward biased. Forward bias means P should be connected to plus supply and N should be connected to the negative supply. Then what happens to the current? The current naturally comes like this. Okay, it comes like this and then goes to the battery. I am sorry, it goes like this, it goes up from the base. The current is conventionally the direction of motion of positive charges. Okay, electrons move in the opposite direction. So current goes like this, through the P it goes to N, and to the emitter terminal it comes out, and this is what is indicated by this arrow. If it is a PNP, then the arrow should be pointed inwards. Okay, this is one of the popular questions that one asks in interviews, for example. Why is a symbol for a transistor like this? What is the significance of the arrow? Why in an NPN it points outwards, when in a PNP it points inwards? Okay, and then the collector junction is usually reverse biased, that is, N shall be positive and P shall be negative. Okay. This is the connection of a bipolar junction transistor, and what actually happens is that the minority carriers here, I am sorry, the majority carriers, they are electrons. Okay, electrons, since the current flows in this direction, the electrons go in the opposite direction. So electrons are injected into the P type region, which is the base. What happens is these electrons then meet some holes here, so some of them recombine, and this recombination comes as the base current. We will see a little later in the next time, but some of these electrons recombine. The base region is so thin that there is very little time to recombine. The electrons are in a hurry to cross the base. After they cross, they come into the collector region, and in the collector region they are majority carriers. Isn't that right? Because this is also N, and because there is a positive potential here, they are attracted by the collector. Even though the collector base junction is reverse biased, because of injection, because of a flood coming in, it cannot obstruct the flood, it lets the flood in, the flood of electrons. Okay, so the electrons are collected by the collector, and that constitutes the collector current, and therefore the total emitter current, if there was no recombination here, and if all electrons were injected, all electrons emitted by the emitter, if they are all collected by the collector, the two currents would have been identical. Isn't that right? I sub E and I sub C would have been identical, but it is not so because of recombination, and because the total emitter current is not just electron current, it is electron current plus hole current, and therefore and therefore I sub c is usually less than I sub e, and the proportionality constant is denoted by alpha I sub e, and alpha is very nearly equal to unity but not quite, it is not exactly unity. We are at the end of our time, so we will continue this next time.